Log on, tune in, find out. Another good idea from Cambridge.
It's an algebras and irreducible representations of Yangians.
Okay. I will speak about irreducible representation of Yangians. Actually, the subject is very close to the previous talks, but is given in quite different language. And this is joint work with Maxim Nazarov. Let me first remind what is a Yangian. Most people know what is it. So formally it is defined as a associative algebra with infinite number of generators. This is Tij1, Tij2, and so on, which are composed into generating function, and the relation are quadratic and can be written in the form of Yang-Baxter equation. So this algebra is a Hopf algebra. There is a co-multiplication. But what I need, I will develop first the famous Alshansky centralizer construction. So this construction describes a map of the Yangian of ZLM to the centralizer of the ZLM into enveloping algebra of ZLN plus M. The precise formula is written here, so it's certain. This formula actually is a reflection of the generators, of the description of generators of the centralizer by Hermann Weyl. And once this map is given, it automatically gives a construction of a family of irreducible representation of the Yangian. Namely, we start from irreducible representation of GLN plus M and take the space of multiplicities with respect to embedded GLM. Then, since this is a Yangian is mapped to centralizer, the space is automatically equipped with the action of the Yangian, and it is not difficult to prove that this representation is irreducible. And so by the construction, this representation is assigned to a skew Jung diagram, lambda minus mu. However, this is not complete list of irreducible representation of Yangian. The main restrictions there are two restrictions. First of all, the main are that both sets lambda and mu should be dominant weights. The same construction is given by Alshansky and other people, Molev, for instance, for other classical groups. I restrict myself to the symplectic Lie algebra just for simplicity of notation. And the corresponding object is called twisted Yangian. It's again given as an algebra with an infinite set of generators which satisfy quadratic relation written in form of so-called reflection equation. Here and another condition which is additional equation like the equation which separate symplectic algebra inside ZLN. Then, so here it's written the R is as above. The R matrix R tilde is transposed to in one tensor component. So this algebra can be viewed as a deformation of the twisted polynomial currently algebra. So these are polynomial functions with value in GLN which satisfy this twist condition. and this is, was proved actually once you take you can define the filtration, and for the corresponding graded object you just prove that this is an isomorphism for JLN and for SPN also. The same construction holds for this twisted Yangian. To describe this, it's more convenient to choose the basis which is usual for symplectic Lie algebra. So this basis, see, it's the skew-symmetric form is given in this matrix, and the indices are either positive or negative. So the generators are defined like Fij. They are not independent, but still we have the construction. It's written here. So this map describes again the map from the twisted Yangian to the centralizer of one symplectic Lie algebra to another, and again it gives a family of irreducible representation of twisted Yangian. Now again, in both cases we want to generalize Alshansky construction to get more representation of the Yangian, and this is done with the help of the use of Howe duality. So let me first remind the notation here. So I choose the skew Howe duality. So I choose the vector space with the tensor product of two vector space Cm to Mcn, and consider the Grassmann algebra generated by xai. So the first index A corresponds to Cm, the second index I corresponds to Cn. They anti-commute, and moreover I consider the algebra of Grassmann differential operator. So it is a Clifford algebra of the space Cnm plus its dual. So it's generated by this variable xia and the left derivation d by j. Now, for this algebra, we have two embedding eta of the GLM to this algebra and zeta from GLM. They are written by similar formulas. So these are two natural actions of GLM and GLN on the Grassmann algebra. And the statement, which is attributed to Howe, probably sure it's already could be named because it reduces to the Schur-Well duality, that the images of in the Olympic algebra of JLM and JLN are mutual centralizers in Grassmann differential operators. The second dual pair, which I consider here, is concerned to two symplectic algebras. Again, I consider the same space as before. So it is CMN, which is a tensor product of two vector spaces. And now it's convenient to introduce another parameterization of the generators of Grassmann algebra, namely this at P and Q. So this P could be either X or derivations, and Q again as a derivation of X. Then in sorry, so it's sum, so then the embedding of the there is a natural embedding of SPn to this Grassmann algebra, which is given by natural action by rotation of the vector space. But there is another action by quadratic differential operators of the symplectic algebra SP2n, which is in terms of Q and P is written by similar formula, but once you remind what is it, so this is second order differential operators. And again the theorem by how that these images of two enveloping algebra are mutual centralizers in Grassmann differential operators. Now I use this how duality to describe another generalization of centralizer construction. Namely, let me consider the algebra A, which is a tensor product of universal enveloping algebra of GLM and this algebra of differential operators. So we have an embedding, first of all, of diagonal embedding of GLM to this algebra, which is given as written here. But instead of the embedding of second GLN, we now have a map from the Yangian to the centralizer of this algebra with respect to GLM. The formula precisely written here. So in this formula, the generating series of generators of Yangian is mapped to such a convolution. So on the right hand side there stands as usual the action in the Grassmann differential operator, but here we have an inverse matrix of the action of the U plus matrix E, which is composed by matrix units which are generators of GLM.
It is just matrices of size m times.
Yeah, okay. Thank you. That's what I meant.
Thank you. We have another good construction for the second dual pair, symplectic to symplectic algebra. So I remind here, so this is embedding of, this is a map from SP to, sorry. Yes, this is diagonal embedding of SP to M in the direct product of this invariant algebra and Grassmann differential operator. And the homomorphism of the twisted Yangian to the centralizer of this diagonal embedding is given by analogous formula. The difference is that on the second side we have again the second order differential operator, and here is a inverse matrix to the matrix generated by matrix units of SP to M. To comment about these maps, so the first one can be viewed in two ways actually. The first way is you can trace this by maps, by names which are written here. So there are two known functors. The first one is actually attributed to Cherednik and developed by Arakawa, Suzuki, and Tsuchiya, which is a functor from representation of GLM to degenerate affine Hecke algebra. And another functor is due to Drinfeld, which associate to any representation of the degenerate Hecke algebra representation to the Yangian. One can compose these two and sum up over intermediate Hecke algebra and get this result. This is one way. Another way is to use this Alshansky centralizer construction and Howe duality twice. And then we get also the same result. For the second map, we have no construction through the Hecke algebra. The only one we knew is a check that this map can be produced by generalizing Alshansky centralizer construction using Howe duality again. Okay, now we have this description of Yangian as a centralizer, some centralizer. And now my logic will be as follows. I will replace the centralizer by the invariance of certain Weyl group, like in Harish-Chandra isomorphism. And now I described the setting. So this second part of my talk is actually the joint work with Maxim Nazarov and Winberg. Let me remind still about classical Harish-Chandra isomorphism. So there are several ones, but what I use is for enveloping algebra. So Harish-Chandra isomorphism describes the center of enveloping algebra in the following way. We have triangle decomposition of the enveloping algebra. So I use the notation K for certain reason for the algebra. And we have a projection gamma of the enveloping algebra to the Cartan subalgebra, just according to this composition. And the statement by Harish-Chandra is that this gamma maps the center to the invariant polynomials on Cartan subalgebra invariant with respect to shifted action of the Weyl group. The essential part of this theorem is actually the graded version, which is called Chevalier restriction theorem, which says that once you restrict the invariant function on Lie algebra to Cartan subalgebra, you get W invariant function, and this is a bijection. Now I would like to look an obvious generalization of the statement. Namely, I would consider, for instance, in a graded version, equivariant polynomial maps from Lie algebra to find the measure representation of the algebra K. Another the variant which is not graded, I would like to describe the invariant in tensor product of an enveloping algebra and find the Milton representation of K. Actually, this problem is already appear in the theory of real reductive group. So we have a problem of description of the invariance in enveloping algebra with respect to the algebra of maximal compact subgroup. The third problem was solved in some way by Constant and Tirao. So the result could be described as follows. So we have a real complex, real semi-sample Lie group, and and describe what I called. So the invariance in enveloping algebra of so now G we have, and invariance will relate to K. We have a map which from this invariance to the following. We choose a Cartan decomposition of Lie algebra G to compact subalgebra and complement, and so take a abelian maximum abelian algebra, and then we have a map So the statement of Constantin-Tirau was that the image of this map, after certain localization, coincides with invariance of intervening operator by Kuhn-Stein. Now I would like first, before describing the answer, to get some motivation and to show how this answer should look like. So first consider this map, consider the symmetric algebra of the algebra V and some vector space which is a representation of the algebra K. So we have a natural map. So H is a Cartan subalgebra. Just as for Chevallier's theorem, we just quotient the tensor product by the ideal generated by two nilpotent subalgebras. And look to the image. And we can easily compute what's going on for SL2, for instance. Because in this case, the symmetric algebra, as well as enveloping algebra, is described as a center tensored by harmonic polynomials, which are now just the direct product of irreducible representation of dimension of even dimension. Each one is generated by the power of element I. And what we should do, we just once we take a tensor product, we just should compute the image of the invariant of this Uj with the same dimensional representation V. So now I suppose that V is a irreducible model. And just easy computations show that the image will be generated by zero-weight vectors, invariant polynomials, and multiplied by the j power of Cartan elements. And actually, this is what is going on in general case. Namely, for any reductive group and fine-dimensional model, the image of the map, which is this is a classical Harish-Chandra map, it's written here, can be described as follows. It consists of all invariant polynomial with values in zero-weight subspace of V, with the following condition, that for any simple root, the projection of this element to is a typical component corresponding to representations of the even dimensional to j plus 1 is divisible by j power of h. So you see, this is as a variety, it's quite a singular variety in this case now. One can also view the same statement for the enveloping algebra. For this, first we should define first the Harish-Chandra map, and it can be done as follows. Once we have the tensor product and V is a module, so we can equip this tensor product with a structure of bimodal just by this formula, so that the adjoint action will be coincide with the initial action of U of G on V as on of K model. Sorry, that notation. And then we can construct this map again by the same way as for Harish-Chandra. So we need actually now the structure, only the structure of U of K bimodal in this map, nothing more. And we have the same statement, similar to the Chevallier's theorem, which describes the image. Now, the image consists again of all elements of tensor product of Cartan algebra and zero-weight space, such that for each simple root, the projection to isotypical component can be written as follows. So here stands the invariant polynomial with respect to simple reflection, and here is, instead of the power of j, stands this Pohammer symbol. Now I want to my goal now is to rewrite this answer as certain polynomial invariant with respect to Y group somewhere. And this is done by means of Zolobenko operators. Now, what is it? First of all, I would like to localize slightly the Cartan subalgebra. Namely, I allow denominators of the sort. So this is a core root plus integer. And once I have this, again, A is a tensor product of, this is actually bimodal with respect to K. Then I construct first the map from this algebra A to its completion, not completion, sorry, to ring of fraction by this formula. So it's you see it is a series with denominators like here, and here I use a joint action of one generators and multiplication by another one. Then one can observe that with respect to Cartan subalgebra, this map satisfy the following property that sorry, it's slightly mistake. It's not here. It should be written. It's for. It should be written instead of sigma. It should be written h plus. Alpha c of h. Then by means of this property, this map can be extended to the map from the localized algebra to itself. And one can observe that this map satisfies the following property. It sends the ideal, left and right ideal generated by, so it's again some use of notations, n prime sometimes appear n prime from one sort of notation and sometimes n plus. So n prime is the same as n plus, and minus is the same as n here. However, the answer is as follows: that after using this property, one can observe that this property allows to define operators from this coset to this coset, and from the double coset space to double coset space. And these operators C with a check. This are defined as a composition of the operators which is written here, and the action of the simple reflection of the algebra which is assumed to be. Now the theorem, the basic theorem of Zolobenko, which is usually known as the Zolobenko co-cycle statement, can be stated as the following: that this operator satisfy break group relations, which is related to the group the algebra which we start from. Moreover, one can compute the square of these operators, and they are not equal to identity, but they differ by conjugation of Cartan element. However, once we restrict to zero-weight subspace, it will be equal to 1. So on the zero-weight subspace of this double coset space, this is the representation of the white group. Now the statement, which is in our joint work with Windberg and Lazarov, that the Harish-Chandra map establishes an isomorphism of the centralizer and the integer invariant of Zolobenko operators. What I mean? I mean the following, that I consider the elements of this double coset space which are invariant with respect to Zolobenko operator, which are also belong to the zero-weight space, and which are images of the elements of initial algebra, not localized. So I replace now I will work with this algebra Q. Instead of the centralizer, I will use the elements of the double coset space which are invariant with respect to Zolobenko operator. Let me recall what is called Mickelsson algebra. It is more or less, it is very close to W algebras, which were told before, and they are formulated as follows. One of the possible way to describe them. So suppose I have a associative algebra which contains a universal invariant algebra of K, and such that this algebra can be presented as a tensor product with respect to a joint representation of K. And now I consider the double coset space localized as before. And then I claim that the double coset space can be grouped with an associative operator, which is written here. So you insert between two cosets the extremal projector by Asherov, Tolstoy, Smirnov. So this is the precise formula for this projector. And so the statement now, additional to what I called before, is first that Zolobenko operators are automorphism of Mickelsson algebra. And second, that the Harish-Chandra map is a morphism which was defined before, is an algebra homomorphism of centralized algebra and the algebra Q, the set Q, which was described above, this one. Now it is an algebra. In summarizing, I will state that I replace the centralizer by the algebra, by the subalgebra in the Mickelsson algebra, which is invariant with respect to Zolobenko operators. One comment about this statement to those who are familiar to dynamical group. So one can recognize that Zolobenko operators are more or less the same as dynamical group, but the difference is that dynamical group action is usually defined on the space of intervening operators. But here it's quite different spaces. This is space of this is double coset space, and the point is that of course one could go from one space to another, but the generators which are natural in the double coset space are not the same as for intervening operators. They are different normalizations. So in the intervening operators business, you can hardly observe this Harish-Chandra map. It's the theorem is for the statement of the Harish-Chandra isomorphism. This realization is essential.
So you have no poles, yes? This is the difference for intertwining. So if you project to a central character, you will get intertwining operators without poles.
Yes, but no, it's slightly different. Poles, there are also there are poles, but first of all they are controllable, and in the image there are no, of course. It's a Harish-Chandra.
It's a projector. So this is a projection to the universal analytic algebra of the Cartan-Sub algebra, right? No?
This one?
Yeah, P.
No. P is a projector to the space of highest weight vectors, or
In the model projection.
I see.
Yeah.
no,
Thank you.
it's different. No, its basic property is that you see this projector satisfy the property that P and minus is 0 and plus P is 0. And once you look to these properties, you see that it's really defining operation of the double coset space because of this properties. Now I go to the situation which I need from the beginning, from the Alshansky centralizer construction. Again, I remind that to a dual pair, I consider two dual pairs for GLN and 2SP. I attached this algebra which is the product. I have an embedding of one Lie algebra and another Lie algebra. So to this algebra R, and I may now make the procedure of construction of the double coset algebra, Mickelsson algebra, with respect to the first diagonal embedding of G. Now, and now I want to look to the presentation theory of this Mickelsson algebra. It appears that this Mickelsson algebra looks quite nice. First of all, as a vector space is in an isomorphic to the differential operators multiplied by localized Cartan subalgebra, and it has a triangle decomposition. So this one subalgebra is generated by derivative, another one is generated by polynomials. It has a Scholle anti-involution, which is composition of anti-involution in Lie algebra G and Fourier transform in differential operators. And thus we can define the projection of this algebra to Cartan subalgebra, like is usually done for semi-simple algebras, and construct a Shapovalov form with respect to this projection. Namely, we take two elements, take their product with respect to this, inserting this projector, and project to Cartan subalgebra. Moreover, we can evaluate this product with in a certain point of dual of Cartan subalgebra. Here is some. It's convenient for symplectic algebra to shift a bit this weight by the weight is constructed by n over 2. Then one considered this Shapovalov form can be viewed as a Shapovalov as a gradient form on the so-called analog of highest weight model for Mickelsson algebra. Namely, this model is a space of coinvariance of tensor product of Verma model and the natural model which is of differential operators, which is the Grassmann algebra of the initial variables. As a vector space, this model M mu can be identified just with the exterior algebra of the tensor space U, which here I use notation. This U is always and for if mu is generic, the space of coinvariance, as I told, can be identified with a description as a Verma model for Mickelsson algebra, named as a model with one generators and the relations like for highest weight model. And this form is contravariant, it's written here. Moreover, we have a natural scalar product on the space, namely for exterior algebra we use the usual pairing, and then the nice statement is this Shapovalov form actually can be described quite explicitly in this form. Namely, we take two elements of exterior algebra, take the embedding natural, which is written here, to the space of coinvariants, and then the Shapovalov form of these two elements can be written as a scalar product of element x, element y, and we act by to I by the image of projector by a share of Smirnov-Tolstoy, only shifted by the weight. So this is a precise description of the Shapovalov form. And now, with this description, one can see the following. Actually, surely this form, the Shapovalov form, once you look to the expression, could have poles. It is defined only for generic weight mu. However, if we restrict ourselves to the weight lambda subspace of this module, and suppose that this weight is dominant, namely that this usual condition, this form is fine and well defined. And the quotient of this weight subspace over this form is a irreducible model with respect to subalgebra S. It's written here. It's subalgebra in zero weight component, subalgebra of zero weight component of Mickelsson algebra generated by initial elements of the algebra of the weight zero. And moreover, this is a model is irreducible as a model over the image of Harish-Chandra map. So we get already construction of irreducibles for Mickelsson algebras. Now there is another construction of irreducibles which use intervening operators, which also come from Zillegenk operators. Namely, here's a bit technical stuff which concerns to symplectic algebra. Namely, we should, to deal with how duality is with respect to symplectic algebra, we need some isotropic subspace inside this U plus U dual, which generates some ideals in the Grassmann differential, the algebra of Grassmann differential operators. And so this is a generalization of Fermat model. So we consider tensor product of Fermat model over algebra U of G and this natural model over the Grassmann differential operator, which sometimes generated by x, sometimes by derivative, and sometimes are mixed.
So when you take quotient by lambda, you take the quotient by the right ideal generated by lambda?
No, it's, you see, this is a left model over differential operators, right?
Quotient means?
Quotient means the model which is generated by, so this is this is quotient means model over the ring of differential operators. That's it.
Yeah, but it is not quotient by the vector space.
So sorry, here is ideal, of course. Yeah, sure. Sorry. Thank you. And now I use again the Zillegenk operators, which satisfy braid group relation. So they, since they satisfy braid group relation, then choosing any reduced decomposition, we can associate to any element of the while group as a well-defined operator in this quotient space. And then observe that it's how this ideals, which I define the models, how they behave with respect to this Chvabenko operators, and then using this we construct the intervening operator between this Verma model and Verma model associated to another isotropic subspace. Finally, I need, as usual, the longest element of the while group, and use this intervening operator related to the longest element of the while group. Then, once I use this, I can identify the initial model and the image as two contragradient models. Namely, I have the pairing, which is written here. Between them, it's not a general pairing. It's actually more or less the same as written here. Just include this element sigma 0, and then the claim that actually, you see this. This is claim about the connection of structure of models between these two, one M and another M, and moreover, this operator psi sigma 0 is an operator now can be identified as an operator of the Shapovalov form. So once you have a space and the form, you can invert the form and so associate to its operator. Thus, its immediate says that we have an identification. So the kernel of this operator is the same as the kernel of the Shapovalov form, and these are both are irreducibles for dominant lambda. So now, if you want to translate this result to the Yangian, we get the following. First of all, this usually it's formulated in terms of functors, which are f lambda is written. So, which is a functor from G models to Yangian models, and it's defined as follows: we take a model over G, multiply it by standard model over Grassmann differential operator, take coinvariance, and weight subspace lambda. It is will be precisely what I defined before. And another functor which I need for symplectic algebra is looks the same, but instead I take another standard model for actually the dual one for Grassmann differential operator. And what I told before says that we have for if lambda plus rho is dominant and mu is arbitrary, then both this are irreducibles model over Yangian, and not both irreducible. So sorry, that there is an intervening operators of Yangian model, and kernel and image are irreducibles. Now, what is less is just to compute what is it in terms of the Yangian, and it can be done. And one can see that once you start from the Verma model, for instance for JLM, JLN, then application of this functor is a standard model. It is a product of exterior powers of the standard representations shifted by the values of their weight mu. For symplectic Lie algebra, the description is analogous. You also have the tensor product of exterior powers of as a standard representation of GLN, restricted to the Yangian, to the Yangian of symplectic Lie algebra, since this is a subalgebra here. And analogous description takes space for the second functor, The only difference is that here is we take the, instead of exterior powers of standard representation, exterior powers of the dual. So we have a realization of irreducibles for the Yangian, for twisted Yangians, and they are now parameterized by two weights, lambda at mu and dominance condition on lambda plus rho. And I state that we get precisely the list which is given in Molev work for a reducible representation of twisted Yangians. So for to remarks first that irreducibility for JLAN was proved before. It is Akasaki Karshevara and Nazarov Tarasov. But for symplectic algebra, for orthogonal algebra, these are new results. Thank you.
Questions or comments?
So this stuff with Weinberg that you explained, can you do all of this for quantum groups?
We didn't try because the proof is contains geometry so of reductive groups. So the essential statement is a generalization of Chevalier restriction theorem, which is proved by geometric methods. So
Well, in principle,
some invariance.
yes, actually yes.
I mean, in principle, you can take the finite part of the quantum group with respect to the adjoint action. And then this should be the analog of U of G.
Yes, I think it's precisely correct, the statement for quantum groups, but for precise proof, it needs to work a bit.
Because these Zhelepenko operators, they work nicely for quantum.
Yes, that's right. That's right.
Okay, well, we meet again at 11:30 on that clock. Let's thank the speaker.